Hello everyone, this is Sashi, and today we will be understanding Zener Diode model parameters, and then we will be seeing the simulation of the basic Zener Diode circuit to understand the parameters behavior. So, in this video, we will first understand the LTspice model parameters of the IN750 Zener diode, and then simulate its behavior in LTspice to observe the voltage clamping and breakdown characteristics, such as um, Zener breakdown voltage, current and Zener breakdown, saturation current, etc. And then we will go to the simulation of the basic circuit and understanding how the parameters behave in simulation. S- the simulation of the basic circuit will help you understand the forward conduction of the diode, reverse breakdown at approximately 4.7 volt, which is the Zener breakdown voltage of this diode, and voltage clipping and clamping behavior of Zener diode, and current flow through the Zener diode. This video will be helpful for analog electronics engineer, power electronics engineer, and someone who is keen to understand the circuit simulation in LTspice. The simulation tool I am using is LTspice, and the Zener model I am using is IN750. Um, so let's begin. This is the model parameters. I have put that in vertical format, and I will be explaining each one by one to help you better understand what each of the parameter mean. So IS is saturation current, which affects the forward exponential region for very small current when V is less than VD. RS is a series resistance uh, in junction, and it impacts the forward drop at high currents. Then we have CGO, which is zero bias junction capacitance, and it impacts the behavior in reverse bias, especially when we are doing AC and switching. Then we have M, which is gradient coefficient for capacitance, and it is related to junction geometry. Then we have Vj, which is junction potential. It is a built-in potential for all the silicon diodes, which is approximately zero point 0.6 to zero point 0.7. Then we have N, which is emission coefficient, and its ideal value is 1. The higher value shows the model combination losses in diode. Then we have Zener parameters, which will be helpful in breakdown region, which is such as BV, which is Zener breakdown voltage. Um, then we have IBV, which is current at Zener breakdown. It is the current at which breakdown voltage is defined. Then we have IBVL, which is low Zener test current, and this helps model behavior at low reverse currents. Then we have NBVL, which is Zener emission coefficient at low current, and it models knee curvature of breakdown region. Then we have TB1, which is temperature coefficient. It models how breakdown voltage changes with temperature. Here you can observe the temperature coefficient of this Zener diode is negative. It indicates that when the temperature is increasing, we will see the voltage clamping get reduced, the Zener breakdown voltage getting reduced, so the voltage clamping will happen at lower voltage. Then we have reverse emission coefficient, which is NR, and it models reverse leakage characteristics. One important point I would like to say is IBV, which is Zener current at Zener breakdown, which is 20.245 milliampere. Um, we should not operate very near to this current because it will lead to higher losses and not the proper functionality of Zener diode. Let's go to the simulation of the basic circuits. So these are the simulation. I have done two simulations. One is AC analysis and one is DC analysis. um, and so this one is DC analysis, and these are the waveforms for it, and this one is AC analysis, and these are the waveforms for AC analysis. um, Here you can see the DC voltage model the to simulate the DC voltage. I have used a DC sweep function of LTspice, where I am sweeping 0 to 10 voltage in the steps of zero point 0.1. I have series resistance of 100 ohm, and the Zener diode model is IN750. This is the circuit for AC analysis. Here I am using sine wave, whose DC offset is 2 volt and the amplitude is 5, and the frequency I'm using is 100 hertz. Then I have 100 ohm series resistance, and the model is same. Also, you can see here I'm also I have also used temperature. um, I have also used the temperature function to see to show you the temperature behavior on the waveforms. So I have used dot step function to vary the temperature from 25 to 200 in the steps of 25. So I will explain. So this is for DC analysis. Here you can see the green waveform is for input voltage. It is rising from 0 to 10 volt, and you can see the blue waveform. It is for output voltage, which is coming across Zener diode, and you can see it is getting clamped at 4.6 volt around, which is the Zener breakdown voltage of this. Which is the breakdown voltage of this Zener diode, and you can see at the when the Zener diode breakdown voltage is reached, you can see the current is increasing exponentially, um, according to the Zener diode characteristics. Here you can see there are two traces in the same plot. So these two traces are for two temperatures. One is for 25 and another is for 200, which I will explain later. First, let me explain AC analysis. So these waveforms are for AC analysis. The green waveform is the input voltage, the blue waveform is the output voltage, and this slightly dark green is a current waveform. So you can see till the time when the input current is rising, but it has not reached the breakdown voltage, the current is zero. And when the input voltage reaches the breakdown voltage, and the output voltage is clamped at 4.6 volt, uh, the Zener current increases. It starts increasing, and then it reaches um, a maximum point, and then it start decreasing when the input voltage start decreasing, and then again it is zero, and then seems in the negative half the clamping is happening at 0.7 volt, which is the built-in voltage for this Zeno. Uh, and for this one, in this negative input voltage, the Zener is behaving is in forward bias, and the current is increasing, and then when the negative half of the input voltage is coming to zero, the input voltage the current is decreasing. So this explains the AC analysis of this is Zener diode. Here also I have plotted two traces in the same plot. So here you can see the effect of two temperatures. So since this diode have negative temperature coefficient, we will be seeing clamping happening at lower voltage. So if I zoom it, um, though the difference is very less, but there is difference. Here you can see the upper trace is 4.69, and the lower trace is 4.66, 4.67. And here also, if you see, if I have to zoom it, here you can see initially at 25 C, the clamping is happening at 4.7 volt, and at 200 degree C, the clamping is happening at 4.68. So this is the simulation behavior of Zener diode. Um, I hope you found this video helpful, and let me know in the comment section. Hit like and share our opinion on this video. Thank you.